Hope. I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students. Pray you help us as the sea fog descends upon us. Give us strength, patience, perseverance. It will soon be over. And just help us to make the most of this time we have. In your name I pray, Lord Jesus. Amen. Okay, so one of you had a question about my problems. So to find the angle between A and B, what you do is use this formula. A dot B is AB cosine theta. All right? So A dot B, what's that number? It's 3 times 4 plus 7 times 5, which is what? 12, 35, 47. What's A? Well, A is the length of A. So A is the square root of 9 plus 49. That's the length of A. The square root of B. What's the square root of B? Well, the length of B is the square root of 16 plus 25, whatever that is. And then cosine of the angle, I don't know. All right? So cosine theta will be equal to 47 divided by the square root of 58 times the square root of 41. So theta will be inverse cosine of that fraction. And you can do the square root of 58 times 41 if you want. So the point of that question was just for you guys to use the formula for the dot product as it relates to cosine to find an angle, whatever that is. See here, I get. I'm in radian mode. I want to be in degree mode because it's more fun. Where'd you go? Oh, there it is. Cosine inverse of 47. Yeah, 15.46 degrees. Roughly, I mean approximately. So that's how you do part of that problem. Now you guys wondering about how do you find the angle between A plus B and A minus B? Okay, so I did the part you already know how to do. Sorry. But it's just the same. I mean, so what's A plus B? Yeah, 3 plus 4 is 7. 7 plus 5 is 12. A minus B, what's that? Minus 1, 2? All right. So, so if you look at that, right? Well, just for convenience, let's call this thing C, and let's call this thing D, right? Then we can just do, okay, so C dot D is equal to CD cosine of the angle I want, and let's call it beta, you know? And then we just do the same thing we just did for the A and B vectors. Right? That's all. Does that make sense? Okay. Any other questions? Okay. So let's continue talking about the calculus of parametrized curves. So I have a few different things I want to talk to you about today. Parametric curves. So the first thing, definition. if t maps to, let's say, R of t is a path, and t naught is an element of the domain of the path, all right, then the tangent line to the path at R of t naught is given parametrically by the following. Lambda maps to R of t naught plus lambda times R prime of t naught. Now, this is, okay, fine. I guess this notation I'm just now using for you. I didn't use this maps to notation in previous lectures, did I? So don't be scared of it. All I'm saying here is that there's like some parameterization. Let's say I need something other than R because I've already used R. Let's say gamma of t, gamma of lambda rather, equal to R of t naught plus lambda times R prime of t naught. So this is the gamma parametrizes the tangent line that I'm talking about here. Let me draw a picture before I do much more. So we're in the plane. We've got some curve. I mean, it's path, really, right? And maybe here's the point that we're interested in. Right, so a typical point on this path is given by R of t. R of t is the typical point on this path. And we're just trying to describe the tangent line, which would look something like this here. All right? So here, a typical point, this would be like gamma of lambda. This right here in my current language is gamma of 0. All right? Gamma of 0 is R of t naught. So that's the point of tangency. Let's see here. What else can I tell you? In this picture, if I was to draw the velocity vector, right? I'm assuming that I mean, there's different ways you could go here. Let's suppose that the curve goes this direction, all right? If the curve goes that direction, then if I draw the velocity vector at the point of tangency, it looks something like this. All right? So there is actually v of t naught, aka R prime of t naught. Now, of course, the tangent line doesn't have to exist, right? You could have what's called you could have like a critical point. You could have some sort of kink in the curve where the velocity doesn't exist. In that case, the tangent doesn't have to exist either, right? Should I work an example? Maybe? Yeah. So we could find the tangent line at t equals .3. So I've introduced lambda as a separate parameter, right? So the lambda parameterizes the tangent line, whereas t parameterizes the curve. Okay, so we're looking for gamma of lambda in my current notation. So what do we got to do? Pretty simple, right? R, first of all, what is R of 3? 3 plus 2 cosine 3, right? Comma 9 plus 2 sine of 3. So this is the point of tangency, right? This is the R of t naught. So here I'm thinking, in my definition, I'm thinking t naught equals to 3, all right? What's r prime? What's the derivative? The velocity, if you will. R prime of t is what? It's 1 minus 2 sine t, 3 plus 2 cosine t, right? Now, when we're finding a tangent line, do we leave t there? No. We have to evaluate at the point of tangency. This is something you guys have trouble with. I don't know why. But you guys have trouble with this in Calculus 1. You have trouble with it here, and you still have trouble with it in Calculus 3. I know, because Dr. Wang was complaining to me this semester about students not plugging in the point and just leaving this as a variable in the formula for the tangent line there. Very popular mistake, but still a mistake. All right, so we have to plug in t equals to 3 to get the vector which points along the tangent line. Not a big deal. So r prime of 3, 1 minus 2 times the sine of 3, comma, 3 plus 2 cosine of 3. So I guess I should put some angly brackets here to emphasize it's a vector. I mean, I wouldn't take off points if you didn't. Now I have everything I need. Hence, we can look at gamma of lambda equal to 3 plus 2 times the cosine of 3, comma, 9 plus 2 times the sine of 3, all right, plus lambda times the velocity, which is 1 minus 2 sine 3, 3 plus 2 cosine of 3. Cleaning it up a little bit, gamma of lambda is equal to 3 plus 2 cosine of 3 plus lambda times 1 minus 2 sine 3, comma, 9 plus 2 sine 3 plus lambda times 3 plus 2 cosine of 3. And there you go. That is a parameterization of the tangent line to this curve at that point. That's all you got to do. Find the point you're interested in, calculate the velocity at said point, put it together. Now we can do further things like, what are the scalar parametric equations for the tangent line? Right, so like x equals to 3 plus 2 cosine 3 plus lambda times 1 minus 2 sine 3 is the x formula, right? Y is 9 plus 2 sine 3 plus lambda times 3 plus 2 cosine 3. There you go. These are the scalar parametric equations of the tangent line. At r of 3. Questions? Now, I mean, sometimes I don't like to use lambda. Like maybe you don't want to introduce a new parameter. for whatever reason, maybe you still want to use time as the parameter for the tangent line. Maybe you want to parameterize maybe you kind of give a simultaneous parameterization, right? Use a parameter for the tangent line which matches the parameter for the curve itself, right? So if you were going to do that, there's a simple way to change what I did just a little bit to get sort of a, I don't know what the word is. I think I've called it the colliding tangent line, right? If you think about these as separate curves, right? If you think about the red curve as the path of one object, and if you think about the green curve as the path of another object, all right? Where the red curve has time t and the green curve has time lambda, would they collide? Would there be a collision at the point of intersection of these curves? No, there would not. See, because this green curve hits the point of tangency at time 0, right? Lambda equals to 0. So it goes, basically this green curve goes through here at lambda equal to 0 and goes on its way. And then 3 whole seconds later, the red object gets there and goes through the point, right? So these do not have a collision. There's an intersection point here, but it's not a collision point. A collision is when you have two paths, like, check it out. Those had an intersection point right here. That was not a collision point. A collision point is like that. I can't do it. Like that, Same point in space and same time for both of the paths. So these are intersecting, but they're not colliding. How would you find the parameterization for the colliding tangent line? You want to make the parameter for the tangent line also be 3 at the point of tangency. There's a simple prescription. All you do is you just trade lambda for t minus 3 to make it collide. In other words, if I do R2 of t equal to basically gamma of t minus 3, that'll do it. So what is gamma of t minus 3? If you put t minus 3 here, right, all that does is it puts t minus 3 here. You can check it out when you plug in when you plug in time 3, right? What happens here? That goes to 0, and you're just left with the point of tangency. So that's how to make the tangent line colliding. If I ask you to find the colliding tangent line, this is what I'm talking about. That's all. Okay. Okay, so what is the what's the Cartesian equation of the tangent line? Can you guys figure out how to find that? So, what did we just have? Let me just kind of work it out symbolically for you in the general case. It's not that complicated, really. So suppose we're looking at a path, all right? We have a path r of t, which is x of t, y of t, all right? And consider a point P, which is equal to, I don't know, let's say P1, P2, all right? And that's equal to, let's say, r of t naught, all right? So the parameter t naught maps to that point on the path. Assume that the derivative exists there so we can find the tangent line. Then what? Then x, let's see here. As we just discussed, gamma of lambda, which would be, r of t naught plus lambda times r prime of t naught. This would be the parameterization of the tangent line by definition. So let's see here how to say this. So this is equal to, really, the x and the y for the tangent line, right? Let me be a little bit more explicit here. This is P1 plus lambda times A, P2 plus lambda times B equal to x comma y, where what have I done? Where I'm introducing r prime of t naught, all right, the velocity at time t naught, to be the vector AB, just to give it something a little bit more convenient to write, all right? So like in my previous example, my example 1, this right here was A, this right here was B, all right? In your physics course, you'd call it V naught x and V naught y. The x and y components of the velocity at the time we're interested in. So you got two equations, right? You've got y is equal to P2 plus lambda b, and you've got x is equal to P1 plus lambda b. We're trying to find the Cartesian equation of the tangent line, right? So what is the one thing that doesn't belong here? Cartesian is what? X and y, right? So this parameter lambda, we need to get rid of that. Yep.
Should it be a plus 1 for x?
Oh yeah, that's an A, sorry. Indeed. So what I was doing was I'm equating this and that, and then that and that. As you can see, thank you. So let's see here. We can solve both of these. I mean, I guess we can solve the first one. Let's see here. How should I say this? Let us solve. I guess we could solve them both for lambda, right? If you want me to be greedy. Lambda is equal to y minus P2 over B. And this gives me lambda is equal to x minus P1 over A. Put these together, you've got x minus P1 over A is equal to y minus P2 over B. These are sometimes called the symmetric equations for a line in the plane. You see why they're called symmetric? It's because x and y appear in the same sense, you know? But of course, we want like y equals mx plus b, right? So let's solve for that. What do we got? Solve this for y. What do you got? Y minus P2 is equal to b over a times x minus P1, or y is equal to P2 plus b over a times x minus P1. There you go. That's the equation of the tangent line. Tell you what, let me write this in a slightly, let me change notation a little bit here. So suppose our curve, I think if I change notation a little bit, you guys will understand what I'm saying better. Here's the curve. Here's the point of tangency. I'm going to call that point of tangency x1, y1. And I'm going to call the velocity vector by its, velocity vector here of v1, v2. Okay? All I'm saying then, what we've just derived here, this bit of algebra, is that the Cartesian equation of this blue line is y is equal to y1 plus v2 over v1 x minus x1. Of course, that assumes something, doesn't it? I mean, we're assuming v1 is non-zero, right? For this discussion, Can you have the first component be 0 for a parameterization of a, I mean, check this out. If I have r of t equal to t squared, comma 3, you can calculate r prime of t is 2t0, right? Any tangent line to that curve, it's going to be vertical. Wait a minute. I messed it up. Flippity floppity. Try that again. That was horizontal. Here, this one's vertical. I mean, graphically, what we're looking at here is just, x is equal to 3, right? So the curve is just this silly thing. If I was to draw the tangent line there, what would it look like? This is a very silly case. The tangent line is, pick any point you want, the tangent line is the line, right? In Cartesians, the curve is x equals to 3, right? Now, that's not quite accurate here. I mean, let's see, what do you guys want me to make my parameter range here? Let's say for t greater than or equal to 0. All right? Think about that. That's not the whole vertical line, is it? What is it? If you think about it, it's just this piece, right? Because y is equal to t squared, right? Which is greater than or equal to 0. We can't get a negative y. So it's not actually the whole line x equals to 3, it's just the upper half of it. And in this case, this formula won't make sense because the tangent line is vertical. Maybe you've been taught it has infinite slope. I mean, the slope is not defined. So, what I'm trying to get across to you guys is, if you want to talk about the direction of the tangent line, the safest way to talk about it, if it exists, is with the direction vector. The direction vector is this thing right here. This is the direction vector. All right? Also known as what? I mean, it's the velocity, right? This is also the velocity of the path, if you want to think physics-wise. That makes sense no matter which way the curve is going, whether it's going at a slope, vertically, horizontally, any different which way. As long as there's not a kink or a stop in the path, the velocity makes sense and describes the direction of the curve. Cartesian formulas will let you down. Cartesian formulas are labor under the misconception that there's a difference between y and x, right? So there's this defect in this formula that says this doesn't make sense when v1 is equal to 0. Right? Well, tangent lines still make sense when v1 is equal to 0. They just don't make sense as equations of y as a function of x. Right? So, any questions? There's something we can extrapolate from this derivation, which is the following little theorem. Dy dx at the point r of t naught, right, is equal to what? It's equal to dy dt at t naught divided by dx dt at t naught. Now this we could derive using a chain rule argument. Maybe I'll do that here in just a second. But you see that going on here, right? Like this is, I mean, I guess it's a different way of looking at it, but maybe this is, I guess this is a derivation of that. I mean, this is the slope of the tangent line is this thing, right? So that's quote unquote, dy dx, right? At where? At x1, right? Well, let me shut up. My point is that this is the slope of the tangent line is the ratio of the y derivative to the x derivative at the point of tangency. So here's that in a nutshell. Let me work a specific example, which is a little bit less, got a little bit less going on. Suppose we have r of t equal to 3t squared, and then times t e to the t. All right. Find slope of tangent line at r of, I don't know, let's say 2. So the way to do this is pretty simple. You've got x equals to 3t squared. You got y is equal to t e to the t. All right? So you differentiate these. Okay? dx dt, x prime of t if you like. X prime of t is equal to 6t. dy dt, or y prime of t, is what? E to the t plus t e to the t, right? Thus, dy dx, which is the slope of the curve at the point r of 2, is equal to, it's equal to y prime of 2 divided by x prime of 2. That's what the theorem says, all right? Which I've given a plausibility argument for, but I'll try to prove more cleanly in just a second here. But anyway, that's e to the 2 plus 2e to the 2 divided by 12. Or if you want me to clean it up a little bit, we've got e to the 2 over 4, I think. Because 1 plus 2 is 3, and 3 over 12 is 1/4. And so there you go. There's the slope of the tangent line. So if I wanted to write the Cartesian, so y equals to, let's see here, if I plug in time, so like y would be y of 0 plus e squared over 4 times x minus x of 0. This would be how I'd write down the equation of the tangent line. The equation of the tangent line in Cartesian variables, that's 0. X of 0 is what? Oh, cool. Wait a minute. No, I'm not plugging in. Why am I putting 0 here? I'm an idiot. What should I be putting there? 2. Yes, thank you. At least you guys know. All right, so 2. And 2. Y of 2 would be 2 e to the 2. And then their slope, e squared over 4. And then x minus x of 2. X of 2 is 12, right? So there you go. That's the slope of the tangent line. Here's the equation of the tangent line, right? Does this make you feel warmer and fuzzier inside? See, this is not familiar, but I assure you this is a vastly superior viewpoint for what the tangent line is, because this covers every possibility. And it allows you to answer questions like, questions about paths of things colliding and so forth. You can answer questions about collisions and intersections and all kinds of interesting things that you can't hope to describe in this boring world of x's and y's. But whatever. I know it's your happy place. I won't try to take it from you. Let's see here. I may try to make you step outside sometime, so let's see here. So that's pretty simple, right? If you want to find the slope from a parametric curve, you just calculate the x derivative, calculate the y derivative, plug in the appropriate point, and divide them. Good to go. Let me see if I can't derive that for you. So the point is, we've got y is equal to f of x is some curve, right? And then we're saying, okay, suppose you have a parameterization of that curve. What does that mean? What does it mean to have a parameterization of a curve? AKA, there's y of t and x of t functions, right? Such that what? What's the deal with this function y of t and x of t? What can you do to it? We've got y of t, right, is equal to f of x of t. That's what that means. For it to be a parameterization of the curve, it means there's a formula for x and a formula for y, that when you put them into the defining equation of the curve, they work. This is a parameterization. Maybe, fine, here's an example of what I'm just saying. If I have, y is equal to x e to the, x squared e to the x squared, I could have, let's see here, I could have x of t be t squared, and I could have f of x be x e to the x. See then, if you look at f of t squared, what do you get? You get t squared e to the t squared, which is, by the way, what? X e to the x. Ooh, I fail. I was trying to do something interesting, and I have failed. Fine. We'll try it again. It'll be boring. So here's the usual stupid thing. I lack imagination at the moment. Fine, I'm fighting it, but I'll accept it. X equals t. F of x equals to x squared e to the x squared. I mean, it's dumb. So f of t is what? F of t is t squared e to the t squared, right? Which is x e to the x squared. So as you can see, it worked. You're like, you're just setting x equal to t. What's the deal with that? I know. My imagination lacks imagination at the moment. Let me think. Let me try to think of something more interesting. I don't know, but mine doesn't. Currently. How about... No, just let me go on. I'm sorry. All right, so if you have this, and I assure you it can be more interesting than my example, but my example is an example. If you differentiate that with respect to time on both sides, what happens? We get dy dt, right, is equal to what? Well, it's equal to df dx at x of t by the chain rule times dx dt. In other words, we get, df dx at x of t equal to dy dt divided by dx dt, and you put in the appropriate point dependence. That's the theorem. I guess. Well, anyway, shut up. So how would you get the second derivative if you wanted to calculate like y prime prime from the parametric equations? What would you do then? I mean, so customarily this is rewritten, dy. So let me just kind of trade f's for y's. Well, if you want to figure out what the second derivative is, if you allow me to erase what I just did here. Can I erase? Well, let me just work this way. It's pretty simple. Just differentiate this with respect to t. What happens when you do that? You get y prime prime. Well, I better be careful. You get d squared y dt squared, right, is equal to what? It's equal to d dt of this product. So f prime of x of t times dx dt. I mean, I'm rewriting this with prime notation. And so then the product rule takes over. See, you get f prime prime of x of t. And then the chain rule says I have to multiply by a derivative of the inside function. So you get dx dt squared. And then plus f prime of x of t times d squared x dt squared. But the thing is, you can trade this piece right here. We already learned in our last calculation that that's really dy dt over dx dt, right? And so this is what we're after right here. So what we get is we get d squared y dx squared, which is f prime prime, is equal to, excuse me, d squared y dt squared minus dy dt over dx dt times d squared x dt squared. All right? And then divide all of that by that guy. And there you go. That is the formula for the second derivative in terms of the time derivatives of the parametric formulas. You can clean this up. If you multiply the top and the bottom by dx dt, then you get like dx dt times d squared y dt squared minus dy dt times d squared x dt squared, all divided by the third derivative, the cube of the time derivative of x, which is the formula you'll find in your book. Yeah.
That's supposed to be d squared y over dt squared. Did you change it from above, or did you do sort of?
I'm saying that this triple underline thing is exactly d squared y dx squared.
Oh, that is, okay.
And so I'm solving for that. Anyway, if you were asked to calculate the second derivative in terms of parametric things, you would go down this path. So here is what you could use to analyze questions about concavity and things like that, for example, right? All right. This brings us to the study of arc length. So let me show you how to calculate arc length. I'll just go a couple minutes over today, if you guys can forgive me, I hope. I'll try to finish at 4:40. So if we have a curve, right, that goes, say, from here to here, like that, suppose it's a path, really. So a typical point on here would be given by r of t, which again is x of t, y of t, right? If you wanted to approximate the length of this curve, how would you do it? Well, here's what I would say you do. You start, suppose that this is time t. I need some, let's say this is t equal to b. I don't know, I need some language here. let's say this is t equal to the total time, big T, and this is t equal to 0 to start with, okay? And so what I want to do is I want to chop it up into pieces. I want to chop it up into pieces of equal time increments. And if you think about doing that, right, if I chop it up into little segments, right, like this, what should happen if I do equal time segments? I mean, as the time gets, so here would be like T1, T2, this is at time 3, and so forth, right? And let's say that this is the nth time. So delta t, the time increment between these would be what? It would be big T minus 0 divided by n, right? T over n, for what it's worth. And like the jth time would be equal to the total time divided by the number of segments times j, right? What would the length of a typical, if I just look at, a typical one here, suppose I look at this one, after a while there's a break in here somewhere. And so we're looking at something that's going from r of tj to r of tj plus 1. What's the length of that line segment? Well, you can break it down, right? You can look at its x part and its y part. So you got change in the jth change in x, and you got the change in y for this jth thing. And the length, right? The length of this little segment, if you want to call it delta r sub j, well, it should be equal to what? It's going to be the square root of the change in xj squared plus the change in y j squared, right? By the Pythagorean theorem. Do you guys agree? And now I can give you explicit formulas. I mean, delta xj is what? It's equal to x of tj plus 1, all right, minus x of tj divided by delta t, and the change in yj, well, guess what? That's y of tj plus 1 minus y of tj divided by delta t. Right? Oh, I'm sorry. There's no delta t there, is there? I just want it to be there. I guess to be fair, if I'm going to put a delta t there, where else do I have to put it? I mean, the change in x is just what's upstairs. The change in y is just what's upstairs, both of these expressions. So to be fair, if I'm going to put the delta t downstairs, where do I have to put it elsewhere? On the other side too, right? So for these equations to be legit, I need a delta t on both sides. That's on purpose. So what I'm looking at now is the average rate of change in the jth component function, in xj. I'm looking at the average change in in y at the jth time increment, right? Now, what is the, do you guys remember the mean value theorem? Remember what the mean value theorem said? If x and y are differentiable functions, and we're considering the time interval tj to tj plus 1, right? So there has to be some tj star in this interval, given the differentiability and continuity of these functions at the endpoint, right? There has to be a point in the middle where the average rate of change is equal to the instantaneous rate of change. So in other words, this is equal to x prime of tj star for some time. We don't know what time, it doesn't matter. There's some time in there that works, and y prime of t j. And to be fair, star star, I don't know that they're the same time. These are separate applications of the mean value theorem. They could give you different times where the average rate of change matches the instantaneous rate of change. But my point is, this can be rewritten, right, as what? Well, see what I have? So basically I can write delta xj as equal to x prime of tj star times delta t. And I can do the same thing with delta y, right? So I've got the square root of dx dt, if you will, at tj star, quantity squared, plus dy dt at tj star star, quantity squared. And I just decided I'm going to have a delta t squared on both of these terms, so let's just factor it out. So what's the arc length? I argue that the arc length is equal to the limit as n goes to infinity of the sum, all right, of the sum j equals 1 to n of the lengths of the little approximating line segments, right, the zigzag path. This is just a geometric idea I have, which I think is reasonable, right? If you take the curve and you chop it up into little line segments and you let the line segments get shorter and shorter and shorter and closer and closer and closer to the curve, it ought to be that that describes the length of the curve. But on the same token, if, and here's the if, big if the curve is such that it has a path, it has a parameterization where the parametric functions are differentiable on the whole thing, that's important, then I can apply the mean value theorem, and I can simplify this to the limit as n goes to infinity of the sum j equals 1 to n of what? The square root of, dx dt at tj star squared plus dy dt at tj star star squared delta t. Well, what is that? That's an integral, right? That is the Riemann sum. It's the Riemann. Which Riemann sum? It's the integral from 0 to n of the square root of dx dt squared plus dy dt squared dt. And there you go. This is the total arc length of the curve. So next time, we'll actually calculate some of these things for specific things. Like, for example, we'll show the circumference of a circle is 2 pi r, among other things. All right? Any questions? No?
Just kind of funny that in calculus 2, in calculus in general, we can calculate the area of circle 1 before we can calculate the circumference.
Yeah, it is kind of funny. And if you look past everything we did right here, there's a nice heuristic derivation, isn't there? See, because it's really like this, right? ds squared is equal to dx squared plus dy squared, right? So heuristically, just divide by, like multiply and divide by dt, right? And then take the square root, and that's why if you integrate up the little ds's, you get the arc length. But I tried to give you a more careful argument today, as opposed to that heuristic nonsense. It is a powerful heuristic, though. Yeah. Yeah. I don't really see much of the point of teaching arc length before we have parametric curves, because if you look at this reproduces the formula you learned for y and x if you did before, right? If the parameter x is equal to t, what happens to this term? It becomes 1. So you've got 1 plus dy dx squared integrated. That's the arc length for a graph, right? So this is the general formula for arc length in the plane. How would you calculate the arc length of a curve in 3 dimensions? You have an x, a y, and a z. You just add plus dz dt squared. But anyway, sorry. Let me get a... We have a Christmas break before that happens, right? So, yeah. I'm sorry, a holiday break. Oh, wait a minute. Where am I? I shouldn't keep you too much longer. I know you might have protests you need to go to. I don't know, but it's here.
Talking about C or